For decades, independent navigation for the visually impaired relied on tactile feedback and guide animals to manage movement. Modern electronic aids attempt to digitize this assistance, but commercial hardware like OrCam or Seeing AI often requires upfront costs exceeding $4,000, plus recurring subscription fees. To function, these devices offload scene analysis to the cloud. This introduces latency that can be dangerous during active movement. Most commercial tools also provide limited descriptions, often maxing out at roughly 20 to 35 tokens per prompt. While basic obstacle detection can prevent a collision, it lacks the contextual detail a user needs to mentally map the structure of their environment. This creates a financial and technical barrier, leaving users dependent on expensive cloud-based systems or navigating with no spatial context. A recent thesis presents an alternative, a vision assistance system that removes recurring software fees and requires no specialized sensors. Instead of proprietary devices, the system is a software solution designed to run locally on a consumer desktop PC. Local execution eliminates network delays and secures user privacy, keeping images of personal environments off corporate servers. The technical challenge was moving the complex processing of powerful vision language models, often referred to as VLMs, strictly to the edge. This approach generates spatial descriptions averaging 168 tokens, reading the geometry of a scene rather than just firing proximity alerts. Executing this locally creates a conflict. High-tier VLM processing must now function within the memory limits of consumer-grade computers. Solving this tension, achieving advanced spatial reasoning entirely on constrained local devices, makes high-tier assistance accessible through standard consumer hardware. The system's design is dictated by a rigid hardware ceiling, a consumer GPU with exactly 8 GB of VRAM. To respect this limit, the architecture avoids continuous video streams, opting instead for query-on-demand single-frame capture. Once a frame is captured, the system routes data through 3 specialized pathways. Vision Mode Scene handles broad environmental spatial mapping. Vision Mode VQA is engineered for rapid object identification, and OCR mode is dedicated strictly to extracting and reading printed text. No single AI model can handle deep spatial reasoning, rapid identification, and precise text extraction efficiently while staying under the 8 GB memory limit. These constraints forced researchers to build a dynamic, bifurcated architecture that uses 2 different models instead of a single monolithic one. The primary engine for the 2 vision modes is the Qwen3 VL2B model. General-purpose VLMs often fail at assistive navigation because they lack specific spatial reasoning and hazard vocabularies. To adapt the system, researchers used a parameter-efficient fine-tuning process called QLoRa. They trained the model on a specialized corpus of 21,000 samples, focusing on directional language and complex spatial relationships. This alters the model's attention mechanism, allowing it to capture the long-range geometric dependencies of a room. The result merges micro-observations, like a floor-level hazard, with the macro context of the entire room layout. Processing this level of detail is computationally heavy, pushing the absolute limits of the local memory envelope. This specialization allows the model to understand the physical logic of an environment, rather than just listing the objects within it. The high memory demand of spatial mapping creates a bottleneck for the third requirement, reading text. Using the heavy Qwen3 model to read a document would cause significant delays. To maintain speed, the system integrates a second, lightweight model, Florence 2 Small. Florence 2 is built for speed, returning text extraction results in as little as 1 second. To ensure accuracy, Florence 2 is paired with Easy OCR and PyTesseract in a quality-gated fallback chain. This lightweight pipeline is designed for immediate tasks, like scanning medicine labels or reading building numbers on the move. It provides rapid, structured data, while the larger Qwen3 engine is reserved for complex narrative descriptions. Routing text queries to a specialized smaller model prevents system-wide latency and preserves the local hardware resources. The architecture uses dynamic routing to orchestrate traffic between these 2 engines. It automatically selects the correct model based on the user's natural language voice command. Both models run simultaneously on the local machine. Even with the dual model system active, maximum GPU utilization is capped strictly at 67.3%. This intentional 30% headroom maintains system stability and allows for zero-latency audio delivery through text-to-speech. Intent-based task routing is the solution for achieving offline AI autonomy on standard hardware. This architecture was tested with visually impaired participants, achieving a 95% overall success rate, with 97% spatial accuracy and 98% OCR accuracy. Compared to commercial alternatives, the system provides significantly more descriptive depth and operates entirely offline. The mode-based routing strategy alone yielded an 8.4 percentage point increase in total system accuracy. It also resulted in a 39% reduction in OCR character error rates. These empirical metrics demonstrate that a locally run software architecture can mathematically outperform a $4,000 proprietary device. This research marks a move away from hardware-dependent aids and towards software-defined accessibility. Retaining processing on the edge eliminates the privacy risk of sending personal data to corporate cloud servers. This enables true independence based on a mental map of the physical environment, rather than just avoiding immediate collisions. Because it uses standard hardware, this software-only approach is deployable immediately to millions of existing consumer PCs. Proving the system functions within an 8GB envelope also provides the groundwork for porting the architecture to mobile and wearable devices. High-tier navigation is no longer restricted to expensive sensors or cloud-dependent subscriptions. It is now achievable through the coordinated performance of specialized models on local hardware.